Right, Artem, you tell us about machine learning selection of AGN. That's interesting. Let's welcome Artem. Your microphone is muted, Artem.
Okay, now it should be okay.
Yes, we can hear you.
Thank you. Sorry. Okay, so common way to select AGNs in the NEP data and in AKARI NEP data in particular is to apply the mid-infrared selection based on color limits to the AKARI measurements described by work of Lee and others from 2007. This method is very effective, however, it strongly limits the size of available data due to the necessity of mid-infrared detection. The question we answer in this work is, are we able to recover properties of such mid-infrared based AGN selection using only optical and near-infrared information? And we do this by incorporating modern machine learning techniques. For this purpose, we are using the new Subaru HSC and NEP-Wide data described by Songjin Kim earlier. This data set is well suited for studying AGNs, and it also has some properties that will have data products of upcoming surveys such as LSST and Euclid and their synergies in particular. We used five bands from HSC instrument and 3 near-infrared passbands from AKARI. Since we are using here supervised learning, we have 2 main samples. One of them is the training sample, where we have known classes of objects. In this case, these are galaxies or AGNs. And the second sample is the generalization sample with unknown objects. And from this sample, we are trying to select our AGNs. In the training sample, class labels were based on the spectroscopical and X-ray measurements. And what is quite important for this work, spectroscopical labels were based on the target pre-selection, which was incorporating Lee mid-infrared based selection. On the right side, you see the distribution of training data in the magnitude color plot of AKARI passbands. So as you see, AGNs type of the first type, they occupy the red part of N2 minus N4 color distribution. This occurs due to the power law feature of AGN SED. The same place is also occupied by high redshift star-forming galaxies, which are the main contaminant for this type of AGN selection. X-ray AGNs are scattered all over the place, also in the areas which are occupied mainly by galaxies. First, in our work, we selected features that are most suitable for this particular task. And to do this, we applied Kolmogorov-Smirnov two-sample test, which simply compares how similar are distributions of 2 different samples. In our case, these are the AGN training sample and galaxy training sample. And we used all possible color combinations and magnitudes, and that way we obtained 8 features that are important for such a classification. We used different supervised models for classification. These were linear models, nonlinear models, tree-based algorithms, and also different voting schemes. Since our data set is unbalanced, so we have much more galaxies than AGNs, it is also worth to try not only basic type of models, but also their class balanced modifications. So we also tried class balanced modifications of all of these classifiers. We also applied two different fuzzy logic techniques. One of them was based on measurement uncertainties, and it penalized the importance of training samples which were poorly measured. And the second one was based on the distance of these objects from the class center. So this fuzzy logic technique is penalizing impact of outliers on the classification. We also performed set fitting analysis in our work, but it is present in our paper, which will soon be submitted and is finished, but is not present in this presentation. Okay, so one thing I want to mention here, which is often, which is rarely used in astronomical application of machine learning, is the generalization sample limit. So since we are working on a supervised learning, our classification can be only as good as our training sample is. And we really should avoid extrapolating our classification during generalization outside the training sample range. So if we have, let's say here we have some area covered by training sample, we really cannot control its performance outside this area. We cannot control the performance of classifier. So simple color or magnitude limits are not the solution for this problem, since even when we apply such cuts, we still will have some areas where our classifier will have to extrapolate. To minimize this problem, we applied a minimum covariance determinant algorithm, which is fitting the n-dimensional ellipsoid to the training sample shape, and then we can limit our generalization sample to the shape of such ellipsoid. Also, since we have unbalanced data, we need to properly choose metrics to evaluate its performance. Simple metrics such as accuracy cannot really be properly used in such case. It will simply show us overestimation of performance, giving us good result on paper. However, it will not tell us too much about the real performance of classifier. Here we used precision and recall metrics, which are focused on the AGN class. So precision shows us the purity of the AGN catalog, and recall is showing us the completeness of AGN catalog. F1 score is the harmonic mean of precision and recall, and we also use the balanced accuracy. During training, which was using specified grid search technique, we were also additionally trying to maximize the F1 score. On the right side, you see the metric values for different types of classifiers. And also below that, you see the F1 score for different types of classifiers. On the left corner, you see the legend. So here you see the performance of different fuzzy logic techniques. And as you see, application of fuzzy logic has a major impact on classification. It's not only the minor tuning. So once we selected the best classifiers, we use all fuzzy logic modifications of them, and then we applied them to the voting technique, which just is taking the majority vote of all of these classifiers. And this way we obtained the final model, which is characterized by the 73% precision, 64% recall, and 80% balanced accuracy. After performing generalization, we obtained a catalog of 465 new AGN candidates. They are marked here by yellow squares, and as you see, they are properly recovering main AGN center. They are recovering most of type 1 AGN. True positive class is the properly selected AGNs. so they are covering red part of N2 minus N4 distribution. False positive are the galaxies which were selected as AGNs. So these are those high redshift galaxies which are the main contaminant for us. And false negative examples are the AGNs which were classified as galaxies, and these are mainly X-ray AGNs. We also performed additional experiment, which was using only these false negative examples as a AGN training sample, and we also used mid-infrared measurements for this experiment to try to select these particular objects, but it also showed quite poor results, so it's really hard to extract these objects with the particular training sample. Okay, we also compared our method to this color cut method. To do this, we limited our sample to objects which have detection in mid-infrared. So out of 1,500 labeled objects from training set, we have now only 800 objects. So due to this power law feature of AGN SED, AGNs are supposed to have very red colors in mid-infrared. So according to Lee work, they should occupy this upper right square. And as you see, our final catalog, which is marked here by yellow squares, mainly also occupy this place, as well as training sample of AGN type 1 marked by black crosses. This light blue color showed the result of this experiment with adding mid-infrared data and to try to recover these X-AGNs. As you see, we selected here some sort of intermediate type of objects. We also calculated features for this for both of methods on this limited sample, and as you see, those values are very similar. Lee and others method is slightly better in recall, so it has higher completeness than the new method. However, our new method has a slightly higher purity than the color-based method. So both metric values as well as color properties are showing that these two methods are consistent. However, only 24% of our AGN new catalog have detection in mid-infrared. So to summarize, it is possible to reproduce mid-infrared based like AGN selection using only optical and near-infrared data. We showed that these two methods are consistent, and well, now in new methods, since it is able to operate in a higher volume data, is a good alternative for mid-infrared selection of AKARI AGN candidates. Thank you.
Okay, thank you, Artem. Now the session is open for questions, comments. Anyone? Any online questions or comments? So maybe I can start. So you didn't use mid-infrared for machine learning, right? But still, you got in a mid-infrared color plot. Still, you had your AGN in a mid-infrared color box area.
Mm-hmm.
So if you use mid-infrared in your machine learning, would it be more efficient? Would you expect?
If we would use mid-infrared data, it of course will be more efficient in the sample which has mid-infrared data. The point was to try to overcome this sample limit of necessity of having this mid-infrared measurements. So the way we did it is actually, since spectroscopic sample that is used to obtain training labels, it is based on Lee method, we are indirectly incorporating information that is that is placed in this spectroscopic sample to our classification. So that is mainly what our machine learning system is doing.
Okay. Any other? Okay. Something has a question. You use cigar result. What does that mean?
Yeah, okay, so it's a broad topic, so I didn't want to cover it. Okay, so we used AGN model from Scritor, and this work was done by Kasia Małek. So what we found that, well, said fitting defined AGNs selected by SED fitting are totally different objects than, are different class of objects than those AGNs that are selected by spectroscopic observations. So we cannot really fully compare the selection based on the spectroscopic data with the selection based on SED data. It also showed us that that our final catalog is mainly consists of AGN with probably some part of some number of contaminations coming from galaxies. We also see that it might be the way out of the to increase the performance of classification by incorporating into the training sample such a template SED-based objects to the classification.
Okay, something. Okay. So thank you.
Can I ask one other question? So maybe you discussed this, but is it true that your success, which seems good, using optical near infrared, is largely based on Seyfert type 1, broadline AGN, and I don't know how many narrow line Seyfert type 2 you have in there, but I guess that the success is pretty low for those because they don't look so unusual.
Mm-hmm.
I mean, it maybe doesn't work very well. I don't know. Did you separate and just look at that?
Okay, so we didn't look particularly on that problem. However, yes, I agree with you. We do not have narrow line AGNs in our training sample. So
Artem,
it's really hard to find them.
Artem, if I may intervene, if you remember when we looked at the Seagal results, yes, we did look into this problem, and actually that's exactly what we see, because this is the limitation of the training sample. So that's exactly the case, and we cannot overcome it.
Until we get some more Seyfert 2s into the training sample. Okay, that's fair.
Okay.